So special functions. So in special functions, we'll study about Bessel functions and Legendre functions. But before that, let's give some definitions too related to a differential equation. So consider a homogeneous linear second order differential equation of the form a2 of x y double prime plus a1 of x y prime plus a naught of x y equals to 0. So this is the general structure of a homogeneous linear second order differential equation. And let's give it the name equation 1. Then dividing each term by a2 of x, we obtain y double prime plus a1 of x over a2 of x y prime plus a naught of x over a2 of x y equals to 0. Then we can let p of x to be this quotient a1 over a2 and let q of x be this quotient a of a naught so we have y double prime plus p of x y prime plus q of x y equals to 0. Let's give this one name 2. So we can say 2 is the standard form of equation 1 after making the coefficient of the second derivative to be 1. Now, with respect to the standard equation 2, we will define the term ordinary and singular point with respect to the differential equation 1. This one, this 2. So definition, ordinary and singular point. So a point x naught is said to be an ordinary point of the differential equation 1 if both coefficients P of x and Q of x in the standard form 2 are analytic at this point x naught. Now, a point that is not an ordinary point of equation 1 is said to be a singular point of differential equation 1. So D means differential equation. So if both P and Q in standard form 2 are analytic at a point x naught, then we say that that point is an ordinary point. But if both P and Q fails to be analytic at the point x equals to x naught, then x naught is said to be a singular point. So just to make things clear, a point x equals to x naught is said to be analytic okay, so let me a function so a function is said to be analytic at a point x equals to x naught if it is continuous at x equals to x naught and if it has derivatives of all order in some open interval containing the point x naught. Or if you remember what you did in engineering 2 in second year, you can say a function is analytic at a point x equals to x naught if we can define a power series expansion that converges to the function in a neighborhood of x equals to x naught. So from a layman point of view, we can understand an analytic point by simply saying that it's a point where the function is continuous and then is fully defined. So examples. So let's do examples or define some ordinary and singular points for some specific differential equations. One, the differential equations y double prime plus y equals to 0 and y double prime plus 3y prime plus 2y equals to 0 have no singular points. That's to mean that for any given value of x, all these differential equations will be defined. So if you are to get the p of x and q of x in both the two functions, you see that both of them are analytic for any given value of x you pick. Number two, if I have y double prime plus e power x, y prime plus sine of x, y equals to 0, then what is my p of x in this case?
E of x.
E power x, correct? And what is q of x?
Sin x.
Sine of x.
Sine of x. Now, are sine x and e power x analytic functions? That's to mean that are those functions continuous and differentiable for every value of x?
Yes.
Yeah. So since both p and q, since both e power x and sine of x are analytic, at every finite value of x, the differential equation every value of x is an ordinary point. That simply means that there is no value of x that will make e power x and sine of x to be non-differentiable or non-defined. So there's no singular point for those for this given differential equation. Now, number three, if I have the next set of differential equation, is it true that, okay, so the first thing we have to identify p of x and q of x. So p of x in this case is x, and q of x is given by ln of x. So the question is x equals to 0 an ordinary point?
No.
Why?
Because value of q of 0 is not defined.
Yeah. So you see that the function, despite the fact that p is analytic at x equals to 0, that's simply that we can differentiate this function is continuous at 0. the value of ln of 0 is not defined. So the function is not analytic at x equals to 0 for q. So this is analytic. Analytic at x equals to 0, but this one is not analytic at x equals to 0. So remember, the condition for the point to be ordinary is that both p and q must be analytic at the specified point. So therefore, x equals to 0 is not an ordinary point. So when we say it's not an ordinary point, what do you mean? Saying not ordinary implies
Singular.
singular. So that means that x equals to 0 is a singular point. Then number 4, what is the singular point of this differential equation x y double prime plus y prime plus xy equals to 0? So to be able to answer that question, you write the equation in standard form such that the coefficient of y double prime is 1, and then see which values of p and q make either p and q non-analytic, or simply which makes p and q non-defined, non-continuous at some specified values of x. So when you convert this differential equation into standard form, we say we'll get y double prime plus 1 over x, y prime plus y equals to 0. So which means our p of x is 1 over x, and q of x is
1.
1. So is q of x analytic? Does it mean that is that function differentiable at any given value of x?
No, not at 0.
So if you say 0, then it's differentiable then. So remember, q of x is analytic for every x. But what point makes q of p not analytic? Or which point makes p discontinuous?
X is equals to 0.
0, yes. We see when x is 0, then this quotient or this rational function is not defined. So x equals to 0 is a singular point. What is making us to say that is because for this function p, we have 1 over x. So the point where the function is not continuous, the function is not analytic at the same point. So which means that point is an ordinary, is a singular point. So x equals to 0 is a singular point. Same question, number 5. Find the singular point if any in this differential equation x squared minus 1 y double prime plus 2x y prime plus xy equals to 0. So the trick is to convert the equation into standard form and then reason out which points where does the function become discontinuous. So that will help you to get the singular point.
X is equals to 1.
X equals to 1. Only 1?
-1 and 1.
These are two answers, okay? Yeah, they should be negative and 1 because the first thing you divide through by this coefficient. So you have y double prime plus 2x over x squared minus 1 y prime plus 6 over x squared minus 1 y equals to 0. So which means that our p of x will be 2x over x squared minus 1. Our q of x is 6 over x squared minus 1. So the singular points are points which make the both p and q discontinuous. And if you remember from your calculus work in first year, if you have a rational function, then to get points of discontinuity, you simply equate denominator to 0. So x squared minus 1 equals to 0 makes this this ratio to be undefined, and this will be x squared equals to 1. So x will be plus or minus 1. So there are 2 points, x equals to minus 1 and x equals to plus 1 are singular points, which mean that are points where the function is discontinuous or simply where the function is not analytic. Now, a singular point sometimes is called regular or irregular with respect to the values of p and q. So a singular point is said to be regular if the functions x, also a singular point, so we're referring to x equals to x naught, x minus x naught. If I multiply by p and x minus x naught squared multiplied by q are both analytic at x naught. Otherwise, if that's not the case, x equals to x naught is an irregular singular point. So a point which is singular, but by multiplying it, multiplying p by x minus x naught and multiplying q by x minus x naught squared, then makes the point to be a regular singular point. If that's not the case, we have an irregular singular point. So we can do an example to see how to determine singular and regular and irregular singular points. So in form of a question, find a regular singular point of the differential equation 2x squared y double prime plus 3x y prime plus x squared minus 4 y equals to 0. So you are always a trusted team. So I want you to help me get the singular point first before we narrow down to determine whether it's regular or irregular. So help me determine the singular point first. So once you get the singular point, we'll use it now to check whether it obeys the conditions on being a regular singular point.
X is equals to 0.
X equals to 0, correct. So you do that, you get the first thing is to determine the singular point by simply converting the equation into standard form, and then find points where the either P or Q are discontinuous, or where the functions are not defined, P and Q. So this divide through by this coefficient to have y double prime plus 3x over 2x squared y prime plus x squared minus 4 over 2x squared y equals to 0. So this means y double prime plus 3 over 2x y prime plus x squared minus 4 over 2x squared y equals to 0. So from which you get your p to be 3 over 2x and q to be x squared minus 4 over 2x squared. So the structure of P and Q is very easy to determine the point of discontinuity, which simply will be the point where the denominator 0. So 2x equal to 0 implies x equals to 0 is a singular point. So which means that our x naught is 0. So remember the same thing, you'll get 0 the same even if you say 2x squared equals to 0 and then so on. So the point of discontinuity, or the point where P and Q are not analytic, is x equals to 0. So let's see. What will be x minus x naught multiplied by P of x? So this will be x minus 0 times P of x, which is 3 over 2x. What does that product give us?
Three over two.
3 over 2. Is 3 over 2 an analytic function?
Yes.
So analytics, so they, from layman point of view, to understand analytics simply mean that is that function differentiable?
Yes.
Yeah. So this is okay. So which is analytic? And then this x minus x naught squared times q is x minus 0, which is our value for the singular point. and then we multiply by x squared minus 4 over 2x squared. What will that give us?
X squared minus 4 over 2.
Correct. X squared minus 4 over 2. Is it analytic?
Yes.
Yeah. So this is also analytic. So which is analytic? Remember, we will have problems if there was an x in the denominator, but there's no x in the denominator. It's just a half x squared minus 2. So that's a differentiable function, even for all x, not just at 0. So now, since x minus x naught p and x minus x naught squared p of x are both analytic, in fact, you can be specific and just, you have already found your x naught is 0, analytic, then x equals to 0 is a regular singular point. Of the given differential equation. So at your own free time, check for this other equation. So find a regular singular point of the differential equation x squared into x minus 2 squared y double prime plus 2 into x minus 2 y prime plus x plus 3 y equals to 0. So try to, the first thing you will get the singular points, and then use the singular points to test whether they satisfy the conditions for regularity of the singularity also. Now, at this point, we now define what we call a Bessel's equation and Bessel functions. So Bessel's equation. So the differential equation of the form x squared y double prime plus x y prime plus x squared minus n squared y equals to 0 is called a Bessel's differential equation. And a particular solution to this differential equation is called Bessel function of order n. So this is our main focus here. If a differential equation takes this form, then such a differential equation is called Bessel's differential equation, and solution to such an equation is called Bessel's function of order n. So I'll not go into the nitty-gritties on step-by-step process on how to find the general solution of this equation. Let me call it star. I'll not go into the nitty-gritties of time, but if you have time, you can always check how the solution is obtained. But once you use the process we call the Frobenius method of solving differential equation, or series method of solving differential equation, you will find that the solution of this equation of star takes the form let me say the general solution takes the form y equals a jn j sub n of x plus b j sub minus n of x, given or provided that n is not an integer, the other form will be y equals to a jn of x plus b yn of x n not an integer, where jn and yn are defined as this is summation so in both cases a and b are constants. So here both a and b are arbitrary constants. So r from 0 to infinity -1 power r over r factorial into n plus r factorial x over 2 raised power 2 r plus n. So this function is called Bessel function of first kind. So Jn of x given by this definition is called the Bessel function of the first kind. So notice that instead of writing this, you can as well write this in terms of gamma function. So the same thing can be written as Jn is summation r from 0 to infinity of -1 power r factorial into gamma of n plus r plus 1 x over 2 to r plus n. This is coming from what you saw on gamma function. You know that gamma of n plus 1. Okay, let me use a different variable so that it doesn't confuse you. So no gamma of x plus 1 is given by x factorial. So you can always change from factorial function to gamma function. So that's why n plus r factorial can as well be written as simply gamma of n plus r plus 1. So I should be aware that when we are defining the Bessel function of the first kind, we can either use the pure factorial notation or we can use factorial and the gamma representation. And similarly, you can define, if you change the argument to be -n, the subscripts, you are going to get the same formula, only that the role of n is taken by -n. So I have -1 power r factorial, gamma of -n plus r plus 1, and then x over 2 2r minus n. So that's how we define j minus n. And then yn is given by j n of x multiplied by cosine of n pi minus divided by sine of n pi. So this is called Bessel function of second kind. So don't be scared by the formulas. When we write come again, there's a question?
You'll give the formulas in the exam.
Yeah. So those will be given to you. But when it comes even to writing the general solution, you don't have to write the whole summations. So they can, so the formula Jn and Yn, the explicit expressions we have given here mostly will help you to prove some identities. But in terms of getting the solution to a specific Bessel differential equation, you write your answer just in terms of the j and y without writing the actual expressions for the j and y. So before we do a specific example, it should be noted that we have said the general solution can be given either by 1 or 2, where y equals to a jn of x plus b j minus n of x, or y equals to a jn of x plus byn of x. So the first case, this will happen, you will use first case when the integer value of n is strictly the number n is strictly non-integer value. But second case, if it's used when, okay, so this doesn't make any sense here. So when n is an integer, so the second case is used when n is either an integer or non-integer. So it's like the second case is the generalization of the solution general. In either case, you can use it to write your answer whether the value of n is an integer or not an integer. N is or even not an integer. So the second case here, where the solution involves the function j and y, will be used whether n is an integer or non-integer. But the first case only applies when the value of n is not an integer. So it should be clear from the word go. When you have studied the equation and you found that the equation is a Bessel differential equation, then each solution or the general solution will be written in this form 1 only when n is non-integer. But when n is an integer, then the solution should be written in 2. But as well, you can use 2 to write the solution even if n is non-integer. It's like this takes care of everything, but the first one only applies when this is non-integer. So probably we can give a very simple example and see how to solve the equation. So for instance, find the general solution of these equations. So the first equation is x squared y double prime plus x y prime plus x squared minus 9. Okay, let me start with the not, let me not go to 9. Let me start by saying, okay, we'll have written 9 over 4, and then y equals to 0. That you can get a half mark or 1 mark. So the key thing, just what is the value of n? In that case,
9 over 4.
9 over. So what did we write in the definition?
3
So
over
it
2.
said a differential equation of the form x squared y double prime plus xy prime plus x squared minus n squared y equals to 0 is called a Bessel differential equation, and solution is called Bessel functions of order n. So remember, the general structure of the Bessel equation is x squared minus n squared, the coefficient of y. So when you relate that to the given problem, what should be the n?
3 over 2.
3 over 2. This is square root of 9 over 4. So this is 3 over 2. So this is not an integer.
3 over
Okay. So this is not an integer. So y will be given by a j 3 over 2 of x plus b j negative 3 over 2 of x. So this is how we write a solution. Or still, you can as well write y equals to a j 3 over 2 of x plus b y 3 over 2 of x. This is still okay. Then 2, if we have x squared, then y double prime plus x y prime plus x squared minus 9 y equals to 0. So what you have to first, you have to understand that the structure of the given differential equation is a Bessel differential equation, and then find the value of n. So what is n in this case?
3.
N is square root of 9, so which is 3. So the solution, so this is an integer. Now remember, when the value of n is an integer, there are no two options, it's only one option. So your solution should be involving j and y, not the first case. The first case is only applicable when the n is non-integer. So the general solution will be y equals to a j3 of x plus b j, okay, y3 y3 of x. So this is the only solution you write. If you write this, then you get it wrong. If you write y equals to a j3 of x plus b j minus 3 of x, this will give you an x, because this structure where we have jn and j minus n only applies for non-integer values of n. So that should be clear from the word go. So there's some useful identities involving Bessel functions. So some identities.
Scroll up a bit.
Okay. Up to a point.
Yeah.
Okay.
Yeah.
So once you're done, you let me know.
I'm done. Thank you.
Good. So some useful identities related to Bessel functions. So one, if you take j of negative n, you will always get -1 power n jn of x. That you can get time and prove that from the definition of the jn function, that j minus n is -1 power n of jn of x. And then number two, j of a half. Okay, j half equals to the square root of 2 over pi x times sine of x. And then it can also be shown that j minus half x is the square root of 2 over pi x, and then multiplied by cosine of x. Like that. So when you are studying engineering mathematics in second year, you must have done what things we call recurrence relations. So where you can express one value of a series in terms of other terms, other previous terms of the series. So we also have recurrence formulas involving the j functions. So if we have, you take x, you multiply by the derivative of jn, you'll always get n times jn of x minus x times jn plus 1 of x. So remember, jn prime means the derivative of the jn function. Number two, if you take x, you multiply by the derivative of jn, the same as negative n times jn function plus x times jn minus 1 of x. And then number three, twice derivative of jn is the same as jn minus 1 minus jn plus 1 of x. And you can always get as many relations as you can. So sometimes some differential equations are expressible in Bessel functions. Or so you can convert some differential equations into Bessel differential equations. So equations convertible or reducible to Bessel differential equations. So there are many which can be transformed into the structure of the Bessel differential equation, but I'll pick this case. If we have x squared d squared y dx squared plus x dy dx plus k squared x squared minus m squared y equals to 0. So here, so maybe I can put in a question. Let me give one. So change 1 into Bessel equation. So what makes the equation 1 not be in the standard form?
K squared.
A k squared is the problem. So if there is no k squared here, then the equation will be already in the Bessel equation form. So we do what we call change of variable. So we'll say let u to be this kx, so that when I say k squared, x squared is the same as u squared. So what we want to do is to transform equation 1 in terms of the variable u and y. So we want to absorb the x variable so that our new equation will be having the independent variable u. Now, if this is the case, then this means that the u, the x will be given by
1/k.
the u dx. So just apply d dx on both sides.
K/1. K/1.
K1, just simply k. It's like telling you what is y equals to 3x. What is dy dx? It's simply 3, okay? But we know that dy dx can be given by dy du times du dx. Which process is this? If I get dy dx in that form?
Chain rule.
Chain rule. So this is by chain rule. So by chain rule, I can always write my dy dx in this form. So which would be the same as dy du, but where there's du dx, I put k. So that means that dy dx is nothing but k dy du. Do we agree on that?
Yes.
Do you agree? So call that one too. So the second derivative is the same as the derivative from calculus. You know that is true, that the second derivative of y is the same as the derivative of the first derivative of y. Okay? Are we together on that?
Yes.
Yeah. So which means this will be d dx. But the place of dy dx from 2, we have k dy du. Okay?
Yes.
Yeah. So we can always factor out the k, which is a constant. So we have d dx of dy du. But if I have these mixed derivatives, I can always, this doesn't matter whether I'm going with respect to x first followed by u, I can as well start with u followed by x. So this can be rearranged as k. So instead of starting with x, I start with u, and then I end up with x. So those are mixed derivative. But we know what dy, the reason that's why I'm using that swapping, or I'm using that property of the mixed derivatives, is because I'm moving away from variable x to variable u. So I want all my derivatives to be purely in terms of the u variable. So this is k, d du. The place where you have dy dx is still k dy du. And when I factor out the k, I'll have k squared, and then d squared y, the u squared. So I can call this one 3. So this is this expression for the second derivative of x, the second derivative of y with respect to x in terms of the new variable u. So replace 2 and 3 in 1. Okay, I call this equation 1, yes, in 1 to get. So remember the first thing in 1, we have x squared multiplied by the second derivative of y with respect to x, which I'm getting my answer to be k squared, d squared y, the u squared, and then plus x, and then dy dx. I've gotten the answer to be k dy du plus k squared x squared is the same as the square of kx, which is the same as the square of u, minus n squared y equals to 0. But if u is kx, what is the value of x?
U over k.
U over k. So I'll have x squared will be u squared over k squared. I multiply by k squared, d squared y, the u squared, plus u over k times k dy du plus u squared minus n squared y equals to 0. So then this allows me to cancel this and this, cancel this and this. So I have u squared, d squared u, the u squared, d squared y, the u squared, plus u dy du, plus u squared minus n squared, y equals to 0. Is that now a Bessel differential equation?
Yes.
Yes. So this is a Bessel differential equation. Whose general solution will be y equals to a j sub n, and then remember now it is in terms of u plus b minus, which is the same as a jn, but u is kx plus b j minus n kx for non-integer u or y equals to a jn of u plus b yn u. Okay, this is for non-integer not used with respect to n. Which is the same as a jn kx plus b yn kx for any u, for any n, whether integer or non-integer. So that's what we do. So when the question is not given in the Bessel form, you can always change it. A small 5 minutes break, we come to finish up.